Introduction to Orbital Motion. Introduction. In this lesson, we will talk about how to use Lagrangian mechanics to derive Kepler's laws of planetary motion. In these laws, Kepler describes the orbits of planets around the Sun. When Kepler discovered these laws back in the early 1600s, he used a purely experimental approach, making predictions from the astronomical observations of Tycho Brahe. He did not know physically why these laws were correct. In fact, it wasn't until 1686, when Newton published his law of universal gravitation, that the physical reason was discovered. That is, it was due to gravity. Likewise, in introductory physics, Kepler's laws are often presented to students as being confirmed by experimental data, and their derivation is overlooked. Here we're going to lay the foundation for the derivation of these laws by defining the Lagrangian for this dynamic system. The learning goals for the lesson will be to first, review Kepler's laws to answer questions about the orbital shape, speed, or period of the planets. Then we'll talk about properties of a central force, and we'll derive the one-dimensional Lagrangian for a two-body central force problem. Your goal will be to understand the steps of the derivation and the variables that are involved. This discussion will be based on Chapter 8 in Taylor's textbook, Classical Mechanics. For more information or more example problems, please use this text. First, we will review Kepler's laws. In the early 1600s, Kepler published his analysis of the astronomical data on the planets taken by Tycho Brahe. He confirmed the Copernican view that the Sun was the center of the solar system and not the Earth, but he also made some very startling discoveries of his own. The first discovery was that the planets orbited the Sun in elliptical orbits, with the Sun at one of the two foci of the ellipse. Before this time, it was believed that the orbits were perfect circles. You probably learned this as Kepler's first law in introductory physics. But one word of caution. Even though the orbits are technically elliptical, their eccentricity is very close to zero, meaning that when you look at the orbit from far away, it should appear circular. Many times you will see drawings of the planetary orbits as skewed so they look more elliptical, as in this drawing of the Earth orbiting around the Sun. This is typically meant to highlight some aspect of the elliptical orbit, say for example that the Sun is at one of the foci. But the distance from the Sun to the far edge of the ellipse is only 152 million kilometers, and the distance from the Sun to the near edge of the ellipse is 147 million kilometers. That's a difference of about 3%. Thus, this drawing gives you an incorrect perception that the orbit is highly elliptical, when it really should be drawn as a circle. The fact that the planetary orbits are very close to being circular was the reason why Kepler's assertion that the orbits were in fact elliptical was so startling. The second discovery was that the orbital speeds of the planets changed depending on where they were in the orbital path. When the planet was closer to the Sun, it moved faster. And when the planet was farther from the Sun, it moved slower. But the planet didn't just move at any random speed. No. It turned out that that speed of the planet was completely predictable as long as you knew where it was in the orbital path. Thus, Kepler was able to figure out a mathematical relationship to predict the orbital speed. This relationship is expressed as Kepler's second law. And at first glance, it seems awfully confusing. The law says that a line between the planet and the Sun sweeps out equal areas in equal times. What this means is that the time it takes for the planet to traverse a particular arc length is dependent on the area of the ellipse swept out by the planet. If the planet is farther away, then for the exact same area, the arc length swept out by the planet will be smaller, and thus the orbital speed will be smaller. In introductory physics, it may just be easier to remember that the orbital speed increases as the planet gets closer to the Sun. But here you will actually want to know the original law, since during class we will be deriving this law from our equation of motion. Finally, the last discovery was that the period of the orbit, tau, was related to the distance of the semi-major axis of the ellipse, which we'll call A. This makes sense since the orbital speed depends on the distance from the planet to the Sun. One way to write this law is to say that the square of the period is proportional to the cube of the semi-major axis. Later we will see that this law will just be a consequence of the second law. Now that we have described Kepler's laws of planetary motion, let's do some problems to make sure that you can answer questions about a planet's orbital speed, shape, and period. Let's do the following two multiple choice problems together. In the first problem, I ask, a planet's orbit is either elliptical, circular, parabolic, or hyperbolic. And in the second problem, the question is, a planet's orbit most closely resembles which shape? We've got a circle, ellipse, parabola, and hyperbola. You should have answered that the planet's orbit is elliptical, but that the planet's orbit most closely resembles a circle. Make sure you have this straight. In the next question, let's ask, if a planet's period increases by a factor of 2, how much did its semi-major axis increase? To answer this question, we know that the square of the period is proportional to the semi-major axis cubed. So to find the new semi-major axis, we can set up a proportion, like so. This will allow us to solve for the increase in the semi-major axis, which happens to be 1.6 times. Finally, in the last problem, I want you to rank the orbital speed of the planet in each section of its orbit, either A, B, or C. A ranking of 1 would be the fastest orbital speed, and a ranking of 3 would be the slowest orbital speed. You should have found that section A had the slowest orbital speed and should have been ranked third. Section B should have a ranking of 2, and section C should be the fastest with a ranking of 1. Hopefully you weren't tripped up by the size of the arcs I drew. Our second learning goal is to find the 1D Lagrangian for a two-body central force problem. By now, you should have a firm foundation in Lagrangian mechanics. We've talked about how to use the Lagrangian and the Euler-Lagrange equation to find the equations of motion for simple systems, such as projectiles, or complicated systems like particles moving on a cone or two masses connected by three springs. Now we're going to use Lagrangian mechanics to find the equations of motion of a planet orbiting the Sun, so that way we can derive Kepler's laws. But we might as well solve the more general problem of two bodies interacting through a central force. In this problem, we have two bodies of mass m1 and m2 that have a displacement r1 and r2 respectively from an arbitrary origin. In the Kepler problem, the first body could be the Earth, and the second body could be the Sun. These two bodies are interacting through a central force. Here I've drawn it as F21 and F12. That is, they are interacting through a force whose magnitude depends on the displacement between the two bodies, the vector r. And this central force has a direction along the line connecting the two bodies. In introductory physics, we might think of this force as a centripetal force. In the Kepler problem, this force is the gravitational force. Let's take a minute and talk about central forces before moving on. Mathematically, central forces are represented as a function of the vector r times r hat, which means that the magnitude of the force depends on the displacement vector and the direction of the force is parallel to r hat, the unit vector that defines the line between the two bodies. Central forces are called central forces because there is a fixed force center. That is, when the displacement vector is 0, the central force is 0, setting a force center. In many cases, the central force is also spherically symmetric. That is, the magnitude of the force only depends on the radial distance r and not on the angular components in the displacement vector. In this case, the spherically symmetric central force is also conservative. You can see this because the force only depends on position, and of course the curl of the force is 0. The inverse is also true, that is, if a central force is conservative, then it's spherically symmetric. For all of the problems we will be discussing, the central forces will be conservative and therefore spherically symmetric. So we assume our central force has the form of f of r, r hat. You should reread section 4.8 on central forces in Taylor if any of this is unclear. Now let's get back to the problem at hand. We have these two bodies interacting via a central force, as shown in the diagram. The goal is to find the Lagrangian for the system so that we can ultimately find the equations of motion. Thus, we might write down the Lagrangian as the kinetic energy of the two bodies minus the potential energy U due to the central force between the two bodies. This Lagrangian, while simple to write down, is a function of 6 coordinates, 3 coordinates for each of these displacement vectors. However, if we choose a different set of coordinates, then we will end up with a Lagrangian that is a function of only 1 coordinate. And this Lagrangian will give us a much better physical intuition about the problem. So let's try to find this Lagrangian that's only one-dimensional. Instead of using the displacement vectors for each of the bodies as our generalized coordinates, let's use the center of mass vector, r, and the relative position between the two bodies, little r, as our 6 coordinates. After all, our potential energy depends on the relative position between the two bodies, and so these coordinates seem like good choices. In this case, our Lagrangian will transform into the following equation, where capital M is just m1 plus m2, and mu, or the reduced mass, is just m1, m2 over capital M. This means that we can think about our original system as having a term due to the kinetic energy of the center of mass, plus a relative kinetic energy term dependent on the masses of both bodies and their relative position, minus the potential set by the central force. What is interesting about this Lagrangian is that all three center of mass coordinates are ignorable. That means that the total momentum for the system is constant and is thus conserved. This shouldn't exactly be surprising. We learned way back in introductory mechanics that the momentum of the center of mass would be conserved. But what is interesting is that if we assume our frame of reference is a center of mass frame, then the center of mass is at rest in this frame, and r dot is 0. Thus, in the center of mass frame, we would then write down our Lagrangian as just the relative kinetic energy term due to the relative position minus the potential energy set by the central force. This Lagrangian only has 3 coordinates instead of 6, which is a drastic improvement. Finally, we notice that the angular coordinates in the relative displacement vector are also ignorable. This means that the angular momentum is conserved. Again, we can define our reference frame so that one of the angular velocities is 0. If we do this, our new frame of reference is a fixed plane in the center of mass frame. Probably when you think about the planetary motion of the Earth around the Sun, you automatically think about movement in this fixed plane of motion. Here, I've rewritten the Lagrangian to reflect the motion in this fixed plane. Movement in this plane reduces the Lagrangian to 2 coordinates. To remove the second coordinate, we can borrow a trick from Hamiltonian mechanics. That is, we can define the angular velocity in terms of the angular momentum L, which is a constant. First, we'll find the generalized momentum for phi and set it equal to the constant L, or the angular momentum. Rearranging for phi dot, we get L over mu r squared, which we can then plug back into our original Lagrangian. Finally, we now have a one-dimensional Lagrangian that defines our two-body central force problem. If we look back at the derivation for how we went from 6 coordinates to 1 coordinate, we notice that it was the presence of the spherically symmetric central force which allowed us to eliminate many of the coordinates. Since the position was only dependent on the relative distance between the two bodies, we were able to ignore the 5 other coordinates. If we were using Hamiltonian mechanics, then that would allow us to reduce the dimensions by 5. However, since we were using Lagrangian mechanics, we had to be more clever. Specifically, we had to move the center of mass frame so that r dot was 0. We also chose a fixed plane in the center of mass frame so that one of the angular velocities would be 0. Finally, we replace the other angular velocity term with an expression dependent on the angular momentum, which is constant, and the relative coordinate. Now that we have this one-dimensional Lagrangian, our goal during class time will be to find the equation of motion for the system and eventually to derive Kepler's laws. Let's do some problems to make sure that you understand how we derive this Lagrangian. In the first problem, let's ask which of the following forces are central forces, and which of the following forces are spherically symmetric central forces. The only force that isn't a central force is the force with a phi hat term. Out of the central forces, the only one that is not spherically symmetric is a force with a theta in the r hat term. Another way to do this problem is to realize that gravity, the Coulomb force, the van der Waals force, and Hooke's law are all conservative. So if they are central forces, then they must be spherically symmetric. And it turns out that all four of those forces are central forces. Interestingly, when we have defined the Lagrangian for a two-body central force problem, we have automatically defined the Lagrangian that describes two bodies interacting via all of these spherically symmetric central forces. Let's do another problem. In order to derive our final one-dimensional Lagrangian, we found that many coordinates were ignorable if we used the center of mass vector and the relative position vector as our generalized coordinates. Given this information, which of the following are true statements about the quantities that were conserved? It turns out that all of the statements are true. The Lagrangian is time invariant, so the total energy is conserved. In addition, the total angular momentum and the total momentum of the system are also conserved, since there are no external torques or forces acting on the system. Finally, the term L squared over 2 mu r squared in our Lagrangian may be new for you. It's typically thought of as a potential associated with a particular force. Mathematically, find the force it is associated with. Can you tell me what the force is physically? To find the force, we need to take the negative derivative of u, which happens to be mu r phi dot squared. This force should look familiar. It may be more familiar if I had written it as a mass times a velocity squared divided by r. It is, of course, the centrifugal force, which would push the two bodies radially outward. Thus, the term in the Lagrangian, L squared over 2 mu r squared, can be thought of as a potential associated with the centrifugal force. We'll talk more about this term when we solve the one-dimensional Lagrangian. But for now, you just need to know the steps for finding the Lagrangian for a two-body central force problem. Conclusion. During this lesson, we have reviewed Kepler's laws and reminded you about how to answer introductory physics questions surrounding a planet's orbital shape, speed, or period. Then we talked about the first step in deriving Kepler's laws, this business of defining a Lagrangian for the two-body central force problem. Your job moving forward will be to understand how we derive the one-dimensional Lagrangian for the problem. During class, we will continue this discussion by finding the equation of motion for the two-body central force problem and talking about the solutions. These solutions are incredibly important for understanding the motions of stars, planets, and galaxies. Plus, some of the most significant questions in physics today, such as the source of dark matter or dark energy, how the universe began, or whether the universe is expanding, stem from measurements of the movements of these astronomical objects. If you're interested in these types of questions, then this unit will be incredibly useful. That's it.